exponential and log shortcuts. So we have a couple rules here. Rule 20, derivative derivative with respect to x of a to the x. That's a to the x times ln a. And another form of this rule, the form that we'll usually be using is a little bit simpler. It's if a is the natural base, which is represented by the letter e, it's approximately 2.7. Then e to the x is its own derivative. E with respect to x of e to the x is equal to e to the x, and that's the form that we'll usually be using. We'll be mostly working with the natural exponential and natural base. And formula 21, derivative with respect to x of log base a of absolute value of x is 1 over x times the natural log of a. And again, we'll mostly be working with the natural log, it'd be base e, and this formula there is a little simpler. Derivative with respect to x of ln of absolute value of x is 1 over x. Okay, so if we want to take the derivative of e to the x squared plus 5, we can do a substitution here. I'm going to do this explicitly. You don't really have to do it explicitly. You can kind of do it in your head if you want, but we'll do a substitution. U is equal to x squared plus 5x, and then so this is going to be f of x. Then with that substitution is e to the u, and f prime of x, the derivative, is going to be derivative with respect to x of e to the u, and we can use the chain rule. This is the derivative with respect to u of e to the u times du dx. And so e to the u is its own derivative. That's going to be just e to the u. Derivative of e to the u is e to the u, and then times du dx. And then we can put the x's back in. This is e to the x squared plus 5x times the derivative of x squared plus 5x with respect to x. So that's going to be e to the x squared plus 5x times 2x plus 5. And usually the algebraic part is written first, so we usually would write 2x plus 5, define 2x plus 5 times e to the x squared plus 5x. Okay, so if we have, here's another example, almost the same except instead of base e, now it's base 2. E is approximately 2.7. It's a long string of decimals. It's one of those numbers like pi that is an irrational number. But here we have base 2, and we could actually use either formula for either the formulas number 20, the one on the left or the one on the right. I'll do it first with the one on the left. So we could do a substitution again. Let's let so this is equal to 2 to the u, where u is equal to x squared plus 5x. So f prime of x is the derivative with respect to x of 2 to the u, and that's we use the chain rule. The derivative with respect to u of 2 to the u times du dx. And then this is what am I doing? This is 2 to the u. 2 to the u. Okay. And this. So the rule for a to u is a to x, a to u times ln a. So this is going to be a to the u. This is 2 to the u. 2 to the u times ln 2. And then times du dx. Okay, so then we could put the x's back in. This is 2 to the x squared plus 5x times ln 2 times derivative of x squared plus 5x with respect to x. And this will be 2x plus 5, so we'll have 2 to the x squared plus 5x times ln 2 times 2x plus 5. And usually the numerical and algebraic part is put first. So I like to write them first anyway. It's just ln 2 times 2x plus 5 times 2 to the x squared plus 5x. I'll also do this using the other formula. So we had in formula 20 we have sort of two different forms of the same formula. So sometimes it's easier to work with the second one, but then we have to convert it. In order to do that, we have to convert it to from base 2 to base e. So I'll also do it using that formula. We do it using that formula. Another piece of paper here. To method 2. F of x is 2 to the x squared plus 5x, and we can convert this to base e. So 2 is going to be e to the ln 2 is the same as 2, and then this is to the x squared plus 5x, because exponential and log are inverse functions of each other, so they sort of can't one cancel out the other. So now we have it in base e. So this is e to the ln 2 x squared plus 5x. And so f prime of x, so now we'll do a substitution. Let's let u, so this is going to be e to the u, where u is equal to ln 2 parentheses x squared plus 5x. Okay, so then f prime of x, I'm doing it that inverse, f prime of x is derivative with respect to x of e to the u, and that's the derivative with respect to u, e to the u times du dx. So that's the chain rule. Okay. And e to the u is its own derivative, so this is going to be e to the u times du dx. And then we'll put the x's back in. That's e to the ln 2 x squared plus 5x times a derivative, I'm having a hard time fitting it on one line, times the derivative with respect to x of ln 2 x squared plus 5x. Okay, okay, so exponential and ln cancel, so this is so we'll just have this is just going to be 2 to the x squared plus 5x, because the exponential and ln cancel. So we'll have 2 to the x squared plus 5x. And this constant can come out, so it's times ln 2, and then times the derivative of x squared plus 5x. It would be 2x plus 5. And then I usually like to write the numeric and algebraic part first, so let's write this at ln 2 times 2x plus 5 times 2 to the x squared plus 5x. Okay. So we could do so these two formulas are pretty much equivalent. You have a choice of either one, but mostly we'll be working with the second one, and we won't be, we'll mostly be working with base E. So anyway, if you have to memorize, I would suggest memorizing the second one, because that's the main one that we'll be working with. X squared, f of x equal x squared ln x. So this one is, we could use rule 21 for this one. This is a natural log, so we'll use the one on the right. We could use the one on the left. We could use either one, but this one is more specific to that problem. Ln absolute value of x is equal to 1 over x. So f prime of x, this is a product, so we want to have x squared times derivative with respect to x of ln absolute value of x plus ln absolute value of x times the derivative with respect to x of x squared. And the derivative of ln absolute value of x is 1 over x. So this is going to be x squared times 1 over x plus ln absolute value of x times 2x. So the x squared divided by x is as x, and this x I like to put in front, so we'll have x plus 2x ln absolute value of x. Okay. This one, I think it's going to be easier with the, we're not going to be working a lot with other bases, but I think this one will be easier if we use the formula for base A. This is formula 21, but we use the formula for base A. And this is the product again. So this is going to be f prime of x is x squared times derivative with respect to x of log base 5 absolute value of x plus log base 5 absolute value of x times derivative with respect to x of x squared. Okay, so this one is going to be 1 over x ln 5. So this is, we'll use the formula 21 on the left formula for 21. 1 over so x squared times 1 over x ln 5. And then derivative of x squared is 2x. So this will be log base 5 absolute value of x times 2x. The x's will cancel here, so we're going to have x over ln 5 plus, and I like to bring the algebraic part in front, we'll have 2x log base 5 absolute value of x. Okay, next example. F of x equal x to the x. Now this one's a little bit tricky because we have an x in the exponent as well as the base. So it's not going to be the power rule. The power rule has x squared or x cubed. They have x in the base but not the exponent. And it's not going to be the exponential rule either, because the exponential has a number in the has a number in the base and the letters in the exponent. So it looks like it could be the power rule or the exponential rule, but it's actually neither one. But there is a way we can handle this, and it's called logarithmic differentiation. So we have y equal x to the x, and then take the log of both sides, and we can use the property of logarithms. Log of an exponential function is the exponent times the log of the base, so that the base can come out in front. So now instead of having a power to a power, now we have a product. So taking the log of both sides, we have it turns the exponent into a product. So now we can use the product rule and use implicit differentiation on both sides. So we want to take the derivative with respect to x of both sides. Derivative of ln y with respect to x equals derivative of x ln x with respect to x. On the left, we want to use the chain rule, so this is going to be derivative of ln y with respect to y times dy dx equals, and on the right side we'll use the product rule, so this will be x times the derivative of ln x with respect to x plus ln x times derivative of x with respect to x. Okay, so then derivative of ln y is just 1 over y, so this is going to be 1 over y times dy dx equals derivative of ln x is going to be 1 over x, so it's x times 1 over x plus ln x. Derivative of x with respect to x is just 1. So we'll have 1 over y times dy dx is equal to, the x's cancel here, 1 plus ln x. Multiply both sides by y, we get dy dx equals y times 1 plus ln x. And then y, if we go back to the beginning, y is equal to x to the x. So this is equal to x to the x times 1 plus ln x. Okay. So that gives us the derivative there. Another example, x to the pi. We can actually use the power rule. I only proved the power rule for integer exponents, but it actually applies to any real exponent. So the old exponent comes out in front, and you subtract 1 from the exponent. So the derivative of x to the pi power is pi times x to the pi minus 1. But we could use the procedure that we just used on that last problem with logarithmic differentiation. Take the log of both sides. The exponent comes out in front, and then take the derivative of both sides, and you get 1 over y dy dx equals, this is just a constant, so this will be just pi times 1 over x, and multiply both sides by y. You get dy dx is pi times 1 over x times x to the pi, and 1 over x is the same as x to the minus 1, so this is just this is equal to pi times x to the minus 1 times x to the pi. So you can combine these two terms here, negative 1 plus pi, or pi minus 1, so that the exponent becomes pi minus 1. So this is actually, we could follow these same steps to prove that this power rule is true for all real numbers. Okay, so okay, here's an interesting example. This one here, you know, if you can solve it for y, you can use just regular differentiation, but this equation here is going to be hard to solve for y. We have x squared plus y cubed times cosine of y equals 17. So so we can use implicit differentiation or logarithmic differentiation. If we use implicit differentiation, so we use the product rule here. Derivative of 17 is 0, but on this side we have x squared times y cubed times cosine of y. So we have to apply the power rule twice. So it's x squared y cubed times the derivative of the cosine plus x squared cosine times the derivative of y cubed plus y cubed times the cosine times the derivative of x squared. Derivative of cosine is minus the sine. Derivative of y cubed is 3y squared, and then you have to multiply by dy dx because it's the chain rule. And derivative of x squared is 2x. So we have two terms with the dy dx. We want to combine those two terms. We can move those across the equal sign, and so we get 2y xy cubed cosine y equal x squared y cubed sine y dy dx minus 3x squared y squared cosine y dy dx. Factor out the common factor dy dx, and then divide both sides by this x squared y cubed sine y minus 3x squared y squared cosine y factor to get dy dx by itself. There's a common factor. Each term has a common factor of xy squared, so we can divide that out and get dy dx is actually we can divide by the cosine y too. So if we divide by cosine y, those will cancel here. This will give us a tangent. So that simplifies the formula a little bit. We have dy dx equal 2y over xy tangent y minus 3x. So that's a logarithmic differentiation. That's implicit differentiation. But we could also do it. Sometimes it's easier to do it with logarithmic differentiation. On this particular problem, I don't think it makes a whole lot of difference. But you can avoid using the product rule at least. But I don't think it will make a big difference. So we take the log of both sides, and so we have use the properties of logarithms. Log of x squared of a product is the sum of the logs. And then the exponent can come out in front. So this will give us 2 ln x plus 3 ln y plus ln cosine y equals ln 17. Well, ln 17, well, whatever that is. Well, we don't need to know that. I'll just leave that. And then, but when we take the derivative, it'll become 0. Okay, so the derivative of 2 ln x will be 2 times 1 over x. Derivative of 3 ln y is going to be 3 times 1 over y, but then we have to multiply by dy dx, but with the chain rule. Derivative ln cosine y is going to be 1 over cosine y, but then use the chain rule again, so it's times the derivative of cosine y. Derivative ln 17, this derivative of the constant, that's equal to 0. So this first term here is 2 over x plus 3 over y dy dx, 1 over cosine y, and then we want the derivative of cosine y, which is minus the sine y, but we have to apply the chain rule again and then times it by dy dx. So sine divided by cosine is a tangent, so we have 2 over x plus 3 over y dy dx minus tangent y dy dx equals 0. We can get rid of the fractions. We have a couple of fractions here. If we multiply everything by xy, that will get rid of the fractions. Xy times x, the x's will cancel, it leaves us 2y. We have xy times 3 over y, the y's cancel, that leaves us with 3x. And then we have xy times the tangent y dy dx. And then we can move the dy dx terms over to the right, factor out the common factor of dy dx, and then divide by xy tangent y minus 3x, divide both sides, to get dy dx is equal to 2y over xy tangent y minus 3x. So it's about the same amount of space. It took me a couple of pages either way, whether we did this implicitly or with logarithmic differentiation. The advantage of logarithmic differentiation is that you don't have to deal with the product rule, and also if you have the letter x in both the exponent and the base, then it's going to be convenient to it's going to be helpful to do logarithmic differentiation. And that concludes this presentation.